Hey everybody, Mr. Piercy here, and what we're going to be looking at today is the reflection piece for the investigation that you did for the angle relationships of polygon investigation. This is just a video to make sure that you're everybody's on the same page and to give you an opportunity to make corrections if you needed to in your thinking and your results here. So let's go ahead and take a look at it. It shouldn't take us too long here. The sum of the interior angle of a triangle. How do I know what the sum of the three angles of a triangle are? Well, you can't say it's 180 because, well, that's what every triangle is. There's a reason for it. It's called the triangle sum theorem. What about quadrilateral? Well, for a quadrilateral, it would have a sum of 360 degrees because, as you can see in the diagram, we're taking the quadrilateral and drawing a diagonal, dividing it into two triangular regions. Since each triangle has 180 degrees in it, the two triangles together gives me a sum of 360. And we can do the same thing with the pentagon. We can see that in the next diagram. How would I know the sum of the pentagon? Well, it has three triangular regions when I draw the diagonals in from one vertex. So that gives me a sum of 540 degrees for a pentagon. So moving on to our table here, filling it in shouldn't have been too challenging, I hope, where you're being able to identify the process very quickly by comparing that there's always two fewer triangular regions than there are sides in the figure. And that's really that process giving us this particular expression here. That's the meat of the that's the heart of this particular example or investigation, making sure that we can get that expression. So write an equation that can be used to model the data in the table. So here, I'm just saying the angles, the sum of the angles, or angle sum, is equal to n minus 2 times 180. There's not this part right here. There's nothing like exactly specific that like it's not going to say y or s or necessarily. So that's why I'm saying angle sum. I'm just trying to be clear, but the way I do it and the way another textbook or another teacher might do it may not be the same. So fill in the table. This is usually where students tend to struggle the most with the application of, so we are looking at this from a geometry perspective, but we can take that information and treat it as a function as we would in algebra. And this is where students have a difficult time thinking it through sometimes. Now the table that you would have generated here should have looked like this, and the points when we plot them out should look like this. Now scale your x and y axis however you need to. I'm counting every two spaces as 1 on the x-axis, and every space up and down on the y-axis, I'm counting it as 90 degrees. So here is the function that you should have seen when you filled in your table, and some students are asking, well, why are we having negative numbers? Well, it's still a function. You know, we can still plug in positive or negative numbers and the function will work. But obviously for us, we're concerned with positive numbers because we're talking about polygons of an actual real physical object. So what type of function is this? Well, the particular function that we're seeing here is a linear function because it has a constant rate of change. The n minus 2 times 180 has a single variable. It has a single letter that's to the first power. So that is a good indication that it's going to have a constant rate of change or a linear function. And you can just as easily count your rise and your run from point to point. And you see, oh, it's the same all the time. So it is a linear function. Will all the numbers be used? Well, no, of course not. Of course all the numbers won't be used. The domain and range of this particular function is all real numbers because it is a line. It's a linear function. But realistically, for our purposes, well, first of all, we can't use negative numbers because I cannot have a polygon with a negative number of sides or a negative angle measurement. And I also cannot use all of the positive numbers because I can't have a polygon that has a portion of a side. I can't have like a 2/3 length of a side. So we can only use positive whole numbers for our sides, and our angles. So that's how we're getting the data here. So that's why I didn't connect the dots in the graph, because this would represent a discrete set of data, or a discrete data set. What would the sum of a 12-sided polygon be? Plug in the number 12 into your formula and you get a 1800 degrees. Here in the next question, we're kind of taking the equation and we're going to work it backwards. We're going to say the angle sum is 1080, so we're given that. Work the equation backwards, divide by 180, and then move the 2 over through addition, and we get an 8-sided polygon, which is an octagon. And finally, is it possible to have a polygon that has an internal sum of 2,430 degrees? Why or why not? In this case, it is not possible. Doing the math, we're going to get the number of sides would have been 15.5. Well, if I have half of a side, I don't have a polygon. Therefore, no, it is not possible for a polygon to have a sum of 2,430 degrees, because polygons have to have a side. They either have a side or they don't. There's no such thing as a half of a side or 5/8 of a side or anything like that in a polygon. So that's pretty much it for our recap of the angle relationships of polygons investigation. Go ahead and let me know if you have any questions about anything, and I'll be happy to work with you on it. But until next time, guys, thanks for watching and take care.